Hi everybody, hope you're well and hope you're nearly ready for Christmas. There's no live lectures this week, but hopefully you've got everything you need to learn this chapter independently. It's all in this video. Lesson objectives over here, and without further ado, let's crack on. So it goes without saying in maths that we encounter a lot of equations, and most of the equations that we've dealt with so far, we have an analytical means of solving them. So for example, these quadratic equations, we know that there's a method of factorization, and failing that, we might use the quadratic formula to solve it. We've dealt with other things like cubics, trigonometrical equations, logarithmic equations, and so on. There's lots that we've dealt with. Now, there are other equations that we haven't quite dealt with yet. For example, this is a cubic equation that doesn't quite factorize. And we can use a numerical substitution to spot that there is a solution. So if I do some minor calculations, if I was to sub 1 into this equation, I would get minus 4. And if I was to sub 2 into the equation, I would get 9. From this information, since plugging in 1 gave us a negative answer and plugging in 2 gave us a positive answer, if I'm trying to solve the equation equals 0, there should be a solution between 1 and 2 that works. At GCSE level, we encountered trial and improvement, which allowed us to tackle problems like this. However, this is going to take a lot of effort and a lot of time, and we don't hone in on the answer particularly quickly. So there is a better way, and we're going to introduce that right now as the Newton-Raphson method. So Isaac Newton and Joseph Raphson, they came up with a good way which combined geometry and algebra together to help find a solution. This plot here, this red line, is the equation x to the 4, take away 2x, take away 3, and we're looking to find the solution here, which is somewhere between 1 and 2. They said was we could work at a point near the root. So you could, for example, plug in 2, it gives you an answer of 9. You could find the gradient of the curve at this point and draw a tangent coming down. That tangent should cut the x-axis, and we can find that point there. Once we've got it, we repeat the process, finding more tangents and more crossings with the x-axis. As we repeat the process, we get closer and closer to the actual root. And even better, Newton and Raphson came up with a way of converting this into a single formula, which you can see on the screen right now. We'll do 1 or 2 examples of this so you can see how it works. Okay, so we're going to try and solve this equation using the Newton-Raphson method. So this is the equation here, x to the 4, take away 2x, take away 3 is 0. And we've been told a value to start with as well. We're told to start with a value 2. Something that you might find strange is we're using x subscript 0 to denote the starting term. But what it means is x1 is going to be the value that we get once we've done Newton-Raphson once. So it kind of works out quite well. So as part of our calculation, we're going to need to differentiate the curve. If I differentiate this, I am going to get 4x cubed take away 2. Yeah, great. And if I take that Newton-Raphson formula, I'm going to use n is 0, I suppose, initially. So imagine n is 0 going into all of this. And if 0 goes here, it's going to work out as x subscript 1. And I get this here. Right. So I'm going to plug 2 in every place, every position here. Anywhere that there would have been an x, I suppose, in the formula. So let's do that there. Let's put 2's in every slot. And I'm going to type that in on the calculator now, and I'm going to see what I get. So let's evaluate. It's going to be in the wrong mode on my calculator. 2 take away fraction. It's going to be the original function on the top evaluated with 2. And on the bottom, it's going to be the differentiated function, again with 2 plugged in it. Right, fantastic. Let's work this out. And it comes out as 1.7. Cool. So that is my first evaluation. So in terms of the function, it means that if I drew the curve very roughly, we've started at 2, we've drawn a tangent, doesn't look quite like that, and the crossing happened at 1.7, and we're then going to do that process again, and we're going to hope to close in on our root. So we'll do the entire thing again with 1.7. So x to the x subscript 2 is going to be x to the 1 take away, and it's going to be basically the same thing again, except I'm going to plug 1.7 in place of all of the 2's in the original equation, something like that. So I'm lucky I've got it saved on the calculator. I'm just going to use this and go back. Need to be careful as well. Some of these 2's were the value being plugged in, like these ones. This 2 here was from differentiating the equation, so that's not going to ever change. That's going to stay as a -2 there. Just realised, sorry, consistency with my notation here. I'm going to write x1 just there. Cool. And now let's calculate it with 1.7s. Awesome. So we've got another answer again, 1.589. So we seem to be closing in on something, and from the earlier PowerPoint slide, hopefully you saw that it was around about 1.5-ish. So this is looking pretty good. We can run the process 1 or 2 more times. I think we get up to x4, so that means that we need to run it twice more, since this is the second value. Something that we can do to make it a little bit easier is we can use the answer button on the calculator. This is great. So because the calculator in its memory has 1.589 as its last answer, what I can do is I can type in answer in place here, and it's going to do the hard work for me. So I don't have to continually retype. I can do something like this. Cool. So I can very quickly get the value for x3, 1.5749. So I'll call it 5. And it seems to be slowing down a little bit as well. We seem to be converging. I'll do it one more time. I just need to hit equals for this. There we go, and it didn't change at all for the first few decimal places. There we go, we've got something like that there, which is great. So here's a second example. This time we've got the equation 4 cos x take away x. And again, from inspection, you can see that the root is somewhere between 1 and 2 again. We won't always have a graph to rely on though, especially in an exam situation. So we'll show it with the change of sign method as well. We'll plug 1 and 2 into this formula just to show that 1's positive and 1 is negative. So let's do that quick. So the original function is 4 cos x take away x. We're going to make sure that we're working in radians as well. So I'll type both of these in. F of 1. Let's see what that is. So that works out as 1.16. So that's positive. That does seem to match here. So that is that's good news. So if we evaluate f of 2, pen's a bit chunky, we're hoping that this is going to come out as negative. And indeed it does. So because of the change of sign, we can infer that there must be an answer between 1 and 2. So we're going to go ahead and use the Newton-Raphson method. So let's jot down the formula for Newton-Raphson generally. To get the next term in the sequence, we take the term before and we subtract the fraction with the original function on top and the differentiated fraction on the bottom. So we are using 1 as our starting term. So x to the 1 is going to be 1 take away the function evaluated at 1 divided by the differentiated function evaluated at 1. And I'm going to be really cheeky here. I'm going to do something on the calculator where I type 1 and hit equals. And what that's going to do on the calculator is it's going to save it as the answer memory. So if I press answer now, it comes up with 1. So I'm going to type in answer, take away, and then there's going to be the fraction. The function, the original function is here, so it's going to be 4 cos, and I want to plug in 1. I'm going to do that by just pressing answer. Take away x, so that's going to be another take away answer on top. Bottom of the fraction, I haven't actually differentiated it yet, so let's make a quick note of what that works out as. The differential, cos differentiates to minus sine, so this is going to differentiate to minus 4 sine x, take away 1. There we go, cool. So that's what's going to go in on the bottom of the fraction, minus 4 sine of the answer, take away 1. Yeah, cool, yeah, I'm just need to verify that that 1 isn't the same 1 as I'm plugging in everywhere else. That's the 1 from differentiating the x up here. So that's fine. Let's hit equals. And this gives me a value of 1.265. Okay, cool, let's write that down. 1.265. There we are, cool, whatever. And that seems to be right, doesn't it? Looking at the graph, if I go up at 1, it's coming down here. Yeah, looks about right. But because I've got this set up on the calculator now, I can just hit equals again, and it's going to generate the second value for me. So let's see, x to the 2. If I just hit equals one more time. Awesome. I've got the next value, which is 1.25. And how many decimal places did I go to here? 5. Okay, I guess I'll do the same here. 3, 8. And if I hit it one more time, I'm going to get a third value in my Newton-Raphson calculations. 235. Awesome. So it looks like, I mean, between these two values, it hasn't really changed much. It's only this 5th decimal place. So we've honed in on an answer very quickly. Looks to be around the 1.251 1.25 mark. We'll just do a quick change of sign, just to verify that the algorithm has worked correctly. You know, we haven't done something wrong. So we'll look at it to 3 decimal places, and we'll go back to the original equation, which was 4 cos x, take away x. And I'm going to plug in values either side of 1.252. So if you think about it on a number line, you've got 1.252 here. If you went up this much, you'd get the value 1.2525. And if you took it away, you'd get the value 1.2515. So we're gonna plug both of those into this equation, and we're gonna see what it comes out as, and we'll justify what that means and why it's important as well. So let's do that one first. Okay, so we get a very small negative answer. And if I plug in, oops, not that, this, I'm hoping that it's going to work out as a positive answer. I'm just looking for that change of sign, really. Amazing, good. Okay, so again, we're mostly just noting the change of sign here. If we were to sort of zoom in on the curve, it sort of implies that the curve does something like this. Can't really see it there, I've vandalized that bit, but that's the idea. You plug in this value, it works out as positive. You plug in this value, and it works out as negative. So the actual answer must be somewhere between this. And if you know your number is between this sort of interval, you know that to 3 decimal places, it's going to round to 1.252. So we have got a correct value for the root to 3 decimal places. Cool. One final note, we've basically covered that topic. Now that is the gist of it. You're going to need to practice it, and there is an exercise just below. One little thing to be aware of is if the equation is not arranged in the form something equals 0, like this, then you're going to need to rearrange it. And it doesn't matter what you do with the signs, as long as there's a 0 on one side, it'll generate the same answer. Thanks, guys.